I'm here to talk about elliptic BLEP, which is a wonderfully ridiculous phrase. My partner refused to believe that it was real. She'd ask me what I was doing for the conference, and I'd just go, blip, 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 and she would think, okay, he's in a funny mood. I'll ask him later. But no, this is the talk. Hi, I'm Geraint. Along with my partner and occasionally this little chap, we run Signalsmith Audio, which is a small DSP sort of consultancy. We do custom algorithm design, bit of code licensing, open source stuff, and a remarkable number of these presentations. I'm going to talk about elliptic BLEP. I'll start with a quick overview of what we're going to cover. So all of this is going to be about waveforms made from polynomial segments. That is the main thing that we're doing today, although there are some surprising applications to that. Then we'll cover what is a BLEP, the general principle of them, some variants and extensions and so on. Practical issues, which means that there are a couple of common implementations people use. And then I'll talk about the related problems that this can also be rephrased as these polynomial segment waveforms. And there's quite a variety of these. And they can be related, a lot of these, if you phrase it right. Then I'm going to take a little detour, talk about Holters-Parker resampling. There might be a better name for this, but this was the paper that I first discovered in when they were carefully emulating a bucket brigade delay, which I've never seen in person. And there's a lot of discrete versus continuous time here, and that's the whole presentation, so brace yourselves. And yeah, we'll talk about doing one-pole filters, then expand that to kind of higher orders. And then we get to the elliptic BLEPs. And we'll generate band-limited impulses, and then we'll integrate them to create band-limited steps and band-limited ramps, and so on. And then we'll look at an example implementation and some C++ code, Python code to design some filters, and then an example of actually using it in practice. So this is a very short waveform made out of polynomial segments. Often you'll encounter BLEPs in the context of oscillators, but as we'll see later, that's not in any way a criteria. That any waveform that is made out of a sequence of segments where each one is a polynomial function is relevant here. And if you've got one of these, you can just sample it, right? You know the function, you know the different segments and the boundaries. The problem is, this is very sensitive to exactly where the samples land in the curve. For different sample positions, it can land one side or the other of this discontinuity, and it's not very good. And actually, as you've got things that line up differently over time, you get inconsistencies, and that's one perspective on where aliasing comes from. Now, ideally, the thing we want to do is to get a band-limited version of this waveform. So we get this and we apply some perfect low pass to it, and then we sample that low-pass version, which, as you can see here, doesn't have this issue where crossing the boundary gives you really fragile and inconsistent behavior. So I'm going to do a little bit of hand-waving here, because I'm going to say that these polynomial curves aren't actually the problem. The problem is the boundaries between them. So here we have a discontinuity, and that's obviously a problem. Here we have a little corner where the gradient changes, and that still, if you played it, would produce a click or thump, which contains a long tail of high frequencies, some of which alias down when you're synthesizing. And this last one's a bit more subtle. It's the rate of change of the gradient. But if you imagine kind of this being a graph of your position in a car, then like that's the acceleration suddenly changing, and you still feel that, and you hear it in a signal. Now, one perspective on what's actually going on here, you can reason about this by thinking about differentiating a signal. This is why I did not put the beginner's tag in this presentation, unlike previous years. So if you have a signal, F, and you differentiate it, that differentiation is a filter. It's a linear filter being applied to the signal, and this is the response of that filter. where the response is proportional to the amplitude. So this means if you have any spectrum, this is a spectrum of your signal, and you differentiate it, then low frequencies, like 0 gets just removed, high frequencies get boosted, stuff in the middle. And if you repeatedly differentiate, if there is any high frequency content at all, then it will, well, at worst get amplified and expand forever, but it will definitely still be present, right? It won't be removed. These ones on the top row, if you differentiate them a few times, they just disappear because they're polynomials, which means we can look at these top ones and say they don't have any high frequency content. These polynomial curves are band limited. We don't need to worry about that section of the waveform. If you differentiate this bottom row, well, right here, you get an immediate infinite spike. Here, if you differentiate twice, you get the same thing. Here, if you differentiate 3 times, and so on. So now we talk about BLEPs. The perfect BLEP, I'm going to explain what it is by explaining how you make it. This is a discontinuity. So we're at 0, and we suddenly jump up to 1. If we, with maths, made a perfect band-limited version of this signal, that's what we want, and we subtract the thing we have from the thing we want, we're left with this little residue, which is the negative of all the bad stuff, essentially. But this waveform here on the right is something we can stamp onto our waveform. At every point, there is one of these discontinuities. You can shift it around in time. You can scale the amplitude to match the amplitude or the distance of the discontinuity, and use that to cancel any aliasing that is in the original signal. And this is the principle of BLEPs. So you've got your polynomial waveform here, and where you've got this big discontinuity, you take your aliasing cancellation residue and you just add it in, centered on that point and scaled so that it matches. But we've also, on the left here, we've got this sudden change in gradient. And actually, we've got a sudden change in gradient at the same time as this discontinuity. So we have to add in that as well if we really want to get rid of the aliasing. And then there's higher orders, and it can go as detailed as you want. And they all have funny names. Given that this is an infinite impulse response one, I did not call this technique BLERP, but I considered it. So the problem with these is that they are infinitely long, right? This band-limited version that we created on the left here, it's based on integrating a sinc function. It just goes on forever. So we have to, in some way, approximate to be able to calculate stuff. BLEP, commonly used because it's cheap and doesn't require much look ahead, but you make a local polynomial approximation to, well, you could say either the ideal version or the residue one here. But you have this little polynomial approximation to this residue, and then you add that in instead. This requires a little bit of look ahead, depending on the order of your polynomial and how many little segments of it there are. And yeah, we truncate the time. And the longer our time is, the more they overlap. If you have lots of these kind of events, gradient changes or discontinuities in a row, then you have a lot of them overlapping, and you have to keep track of when they were, how far ago they were, and then drop them off the list when they're finished. And it's not impossible, it's just fiddly, and I don't like doing fiddly things. So another one is min-BLEP, which is really quite close to what we're doing today, except the way that it's done is you actually generate, as a sampled signal, but like massively oversampled, this step, and then you low pass it with a really nice band-limiting filter, and then you take a little segment out of that, and kind of that cropped version is our cropped residue for canceling the aliasing. This doesn't require look ahead. It is still finite time, but it can be arbitrarily long. Unlike polynomials where the maths gets really sticky as you get into higher orders, this is very simple to extend. to make the impulse response longer. You still have that problem with the overlapping segments and the bookkeeping, and because this is kind of generated as a table, generally then you'll do this sort of polyphase implementation, which again, it's fine, it's fiddly. But yeah, this is generally what BLEPs are. Hopefully that makes sense as a technique, these anti-aliasing stamps that we're sticking on. Now, I'll talk about some related problems, because you might think, well, polynomial waveforms, that's just people trying to make sawtooth waves, right? Why am I interested in that? I do guitar pedals or whatever. So if you are just thinking about your signals as a digital audio developer as an array of numbers, you're going to get in real trouble when you start to consider aliasing, because you'll just be like, well, it's mysterious, it comes from somewhere. I would urge you to consider your signals, even your digital or discrete time signals, as continuous time signals. And the samples are, we know what the value is at particular points in time, and you have to, as part of the interpretation of that signal, define what's happening in between those samples. And I don't know, maybe you're linearly interpolating between them. Maybe there's a nicer, smoother interpolation. Maybe you're just using the nearest sample. And some of you might say, yeah, well, sync curves, obviously, is the correct move here. That's not necessarily true, actually. When you get into spectral processing with STFT subbands or even software-defined radio, you'll find that sometimes these sampled signals are representing frequencies way higher than the sample rate. But the point is, you have to know what is happening in between your samples and decide how these samples extrapolate to continuous time, and then make sure that the calculations you're doing or the interpretation you're using match. Because otherwise you won't understand where your aliasing is coming from, right? And you need to choose a nice, good interpretation of this continuous time signal. Treat your signal appropriately, and then you'll be able to reason about and design better systems for less aliasing. So we're just going to do this a lot. This actually is, I think, almost the last mention of discrete time signals in this presentation. Everything here, from here on, is going to be in continuous time. So, waveshaping, a related problem to polynomial waveforms. So if anyone's familiar with antiderivative anti-aliasing, then this first half might be familiar to you, because you say, okay, I've got my signal, I'll linearly interpolate between them, and then I'll stick the continuous time version of that through a waveshaping function. And then you might think, oh, well, this segment between these two samples exactly matches this segment of the waveshaper, and so I can use the integrals and stuff to find out these samples. We're not doing that, okay, right? We've got this linear interpolation between samples. We've stuck it through the waveshaper. But if our waveshaper is made out of polynomial segments, then our distorted wave-shaped curve is also made out of polynomial segments. You've taken a linear section of signal, stuck them through a polynomial function. The output is just polynomial segments. So if we can solve this polynomial problem, then this gives us quite a nice way to anti-alias digital waveshaping. Plus, because we're now in continuous time and we've low-passed, your output sample rate doesn't have to match your input one at all. So you could, for example, upsample your input, as you might do when oversampling, do this polynomial segment thing, and then instead of sampling again and then downsampling, go directly to your output sample rate. Why not? You can, once you've got this polynomial segment stuff sorted, you can read out this continuous time signal at whatever time positions you want. This is related to the problem of resampling, where if you've got your samples and you generalize to the continuous time signal in some polynomial-based way, maybe a Lagrange or whatever, then you can sample this nice and easily. I mean, you can do that anyway. But you can, the polynomial interpolation you use to get to continuous time here doesn't have to be excellent if the anti-aliasing BLEP-based thing you then use to resample it again is good, right? So our polynomial continuous time thing doesn't have to be nicely, perfectly anti-alias, because we can anti-alias as part of resampling by treating it as this polynomial segmented waveform. Yeah, oh yeah. When you're doing these BLEPs, make sure you band limit to the lower of your two rates. Otherwise, it's pointless. Another problem which comes up a lot when we're talking about synthesis is hard sync, because it sounds rad. But these discontinuities, you have a carrier wave, like a base waveform, then you have this other waveform that's going at a higher rate that periodically gets reset in its phase. And the discontinuities that happen here obviously have a long tail of high frequencies. And this is actually a specific example of phase modulation, which is the same as frequency modulation, just integrated. So that's, again, if your phase signal can be mapped through a polynomial waveform for your oscillator, then that's, again, a polynomial segment output. Audio rate delay modulation. Again, this looks very similar to the waveshaping diagram, except our input is now the waveshaper, and our signal is now the time. All these things, hard sync and distortion and frequency modulation, or weirdly, you can phrase them in the same equations, and it's a very mathematician trick to say, we've solved this one thing, let's translate everything to that. So again, now we're on to this Holters-Parker thing. So I'm going to talk about one-pole filters for a moment. This is a continuous time one-pole filter. We've got an impulse happening at time 0, and then we see the response of this filter just decays exponentially from there. This is really nice because if we know the value at a certain point in time, we can read out any future value very simply, right? We just find the exponential of how much it's decayed and multiply by that. If we have a second impulse, we can find how much it's decayed just here, just before, and then add in a new impulse, and then decay from there. We only have to remember one piece of state, which is the value last time we knew it. And then we can always predict any future value just from one recent historical value. Now, higher order filters, higher order filters, if they have no repeated poles, can always be represented as the parallel sum of one-pole filters. This is maths. Some of these one-pole filters will be complex, so as opposed to just decaying over time, they will in fact spiral in phase as they decay. But that's fine, the maths is all the same, right? It's still an exponential, it's just that there's an imaginary component to that. So yeah, higher order filters can be expressed as the parallel sum of one-pole filters. This means that we can easily read out the value of any higher order filter if we decompose it into these one-pole filters. So there we are. If we have this, the current state at any given time here, then we can jump forward or read out the value for any future time by applying the appropriate one-pole decay to each of the component ones individually and summing up the result. I think this is really cool. Holters and Parker used this to exactly reproduce the aliasing of a particular piece of non-digital but still sampled equipment, which is very cool. But I'm not doing any of that because I'm a DSP person and I like things clean. So now we have our feature presentation, the elliptic BLEP. So if we design one of these high-order filters, which is going to be low passing at, let's say, 20 kilohertz, right? So whatever signals we're putting into it, it will always be ready to sample, and we'll get an alias-free, or almost alias-free, discrete time signal out of this. This impulse, there's an arrow at the top to imply that it's actually an infinitely narrow, infinitely high Dirac delta spike. But the point is, if we integrate this impulse, we get a step function. So presumably, if we integrated this filter's impulse response, we'd get a low-passed step function. That'd be cool. Let's try it. So the way we do this is, again, we've got it as the parallel sum of one-pole filters. And one-pole filters, being exponential decays, are incredibly easy to integrate. You just multiply them by 1 over A, whatever A is, your like decay factor, which might be complex, but that's fine. Yeah, so this should work. This should work, right? Yeah, you can see that if you integrate them all individually, then ideally they'd add up to produce this band-limited or almost band-limited step on the left. Unfortunately, this almost works, right? So we've got our original one. This is the actual implementation from my C++ code. And yeah, the blue solid line is the impulse response. So I've got all these filters running, these one-poles in parallel, and I give them all a kick at time 0, and then just kind of read out the value at various other points. And for the dotted red line, I've given them different amounts of energy added in based on this 1 over A factor for each of the one-poles. And it looks almost right, except I did kind of expect it to start at 0, right? You look at this and you think, well, the integral should start at 0. Maybe that's fine. You integrate it again. It's not even starting at a nice integer value. I mean, so I was expecting also the second integral should be the band-limited ramp, right? The point when we go from 0 gradient to a 1 gradient. And you'd expect that to look something like this. But it doesn't. The actual problem is integration. So I mentioned earlier that differentiation is a linear filter. And this is the response of it. Integration is similarly a digital filter, and it has the inverse response. But differentiation goes to 0 at 0 hertz. So integration goes to infinity. And there's always this kind of like when you integrate, there's this like constant value that's a bit ambiguous and you have to set it somehow. But like this is why things are going wrong. Basically is that like the filter that we're integrating has non-zero response at DC. And so when we integrate it, it gets an infinite amount of energy at DC, which is it's expecting to go at value -1 for, well, most of the time. So what can we do about this? We're going to high-pass it. So if you apply any high-pass, then it will have a 0 amplitude response at frequency 0. If you apply a Butterworth high-pass, for example, a high-order one has repeated zeros, has lots of zeros, like stacked on top of each other at 0 hertz. So it's very 0 at 0 hertz. As engineers and not mathematicians, we are allowed to play fast and loose with infinity. But here we have the idea of some things being more infinite and more 0 than others when you're talking about zero-pole cancellation. So bear with me in this horrendous hand wave. It does work out when you go through the equations, but you can also muddle through with intuition with enough practice. But this works, right? So let's look first at this blue line. This is the original impulse. And this is our filter response plotted as a spectrum. And I've designed this as an elliptic low pass, 0.1 dB of ripple, 20 kilohertz cutoff. And then I've added in a third order here, Butterworth Highpass at 20 hertz. And this gives me 3 zeros at 0 hertz. So it's thrice flat at 0. And this means we can integrate it 3 times before anything goes wrong. So these are the integrated responses for those filters. We can see this 1 over x curve, and there's 1 over x squared, and there's 1 over x cubed happening. That's obvious in this lin log scale, which I've chosen. But yeah, this is, how do I even, there we are. Let's, this is what I get, again, for writing my own slide framework. There we are, okay. So these are the impulse responses that we've now generated by designing our band-limiting low-pass, adding in a high-pass, then doing the decomposition into one-poles, and then integrating those one-poles individually, which just means giving them a little kick with different weights. So it's the same poles happening for all of them, the same one-pole filters, but we give them a different type of kick. And we can get this impulse, we can get its integral. The second and third order ones whiz off into infinity. Well, it's not infinity, because as you can see from this zoomed out one, zoomed out in time and frequency, they do in fact oscillate. They just oscillate very slowly. But yeah, I mean, we high-passed it around 20 hertz. So not insane that the second order one is kind of settling down around 50 milliseconds or so. I mean, that kind of scans. But I mean, this works. You can, if you make sure that the filter you're integrating has a lot of zeros at 0, then you can integrate it to get these continuous time, like arbitrarily addressable filters. So how do you use one of these things? Well, you've got your current waveform output, and then you encounter a boundary to the next polynomial segment, and you say, well, is there a discontinuity? No, there's not. Is there a change in gradient? Yes, there is. So you add in, you give your filters the appropriate level of kick responding to a singly integrated thing proportional to the amount of gradient change. And then you just carry on, because actually the filters, as you can see, are going to handle this ramp up. Like, you don't have to do anything other than just tell it about the boundaries. And then you carry on going until you reach a discontinuity, and then you give them a kick in the other direction with different weightings. And you continue, and that's it. So let's just have a quick look at this is the implementation that I've been using to generate a lot of these graphs. Here are my magic pre-baked filters. These are my poles and the weights for summing them up. And so if you just run these poles as exponential decays and then add them all up, then you get the impulse response. And this is, I'm not going to go through the code because I don't really have time for it. The main reason I'm showing you this is to show you that it's actually quite short. This is quite neat. And if we navigate just up here into this design thing, yeah, you can see that I last commit was 2 hours ago, which shows you how organized I am. Yeah, here we design the filter in Python, and then here we write it out as these C++ coefficients. So this, I think, is neat, right? This can be a nicely elegant solution. And let's go back to the, yeah, great, that'll do. Yeah, so, and you can read through the code later, but essentially you have a current state, a current value for each of our parallel one poles. I've only drawn 2 of them here, but there are loads and they're complex and everything. But there are 2 main methods. One is step forward, which is for each of these states, you move them forward by decaying them a certain amount. You move them forward by a sample or a fraction of a sample or whatever. And then the other method is give it a little kick. You add in an impulse or a step or a gradient change any of these orders based on the change in the first differential or the second differential or whatever it is that you're looking at. And then that's it. Then there's a get method which just adds up all of these states, and that's your output. So yeah, this is it actually in practice. This is a hard synced triangle wave, right? So it gets to 2 3/4 of an oscillation, and then the lower oscillator resets. And so there are little wibbles that you can just about see maybe on the corners. But when there's the big reset, there's a discontinuity. And so you see the anti-aliasing happening there. That's our Gibbs phenomena. We're going to zoom in on just this little section here between 4.5 and 5 milliseconds. And I've actually rendered this same waveform. This blue one is at 44.1 kilohertz. And I've run this exact same code at 96K and at 384K, which is 8x oversampling at 48K. And you can see they line up, right? So what's happening is, because I've used a static filter where the cutoff is always 20 kilohertz, because of the way that I baked in the high pass, so if you scale it, then the high pass gets higher, and that could go wrong. But the point is, even at 44.1K, we are correctly sampling this very smooth, anti-aliased, low-passed signal. And if we look at the spectrum of this, there we are. I designed the filter with minus 100 dB as its stop band ripple. Voila. This is an 11th order elliptic low pass. I can explain why odd orders work better, because even orders have like a bit of a dry signal going through. It's fine. I'll explain if you're curious, either now or catch me later. But yeah, this is the anti-aliasing at work. This is a hard synced triangle wave just made out of polynomial segments. And yeah, I've rushed through this talk. Woohoo! So there's loads of time left. Yeah, so the method that I've used here is, as I showed in the sort of explanation of these step and add methods, we are actually producing the waveform directly by adding up these states. So like, you're not calculating the waveform and then using this stamp to cancel the aliasing, which is the normal way to use BLEPs. Here, it's also generating the actual polynomial curves as well. There are some advantages to this, but the disadvantages are it's high-passed. Maybe you really care about what's below 20 hertz. And also, sometimes you're going to want to hard sync a waveform that's not a polynomial. Like, if you hard sync a sine wave, then most of the time you want to just output the sine wave, and then every now and again there's discontinuity. And then you want to continue just reading out the sine wave. There's not really a way to do that in this system, in the way that I've phrased it here. The classic method is that you would synthesize the version of this hard synced sine wave which would alias, and then you add in this aliasing cancellation layer to it, which is, so you'd output the naive version of it, and then you'd also output this BLEP signal. This is a bit more fiddly, but it's totally possible, right? Like, remember back in the start when I explained what BLEPs were, you create the ideal version, and then you create the kind of naive version, and you subtract one from the other. Because of the high-passing thing we did, what you actually want to do is take the thing that we have, which has the actual big swoops in it, and then also generate this parallel one-pole version of just the high-pass filter on its own. And then you subtract those two, and that will give you this residue. So it's entirely possible. It doesn't cost any more computation to compute. It's just that if all your computing is polynomial segments, then you might as well let this handle it. But if there's any other stuff like the actual sine wave, then you have to go this more complicated method. And then, I didn't really mention this at the time, but it is important. The elliptic low pass has a very nonlinear phase response. So if there is going to be some interaction between, in the case of a hard synced sine wave, there's going to be some interaction between the regular impulses or steps, the discontinuities from the hard sync, and the actual phase of the sine wave. And I don't have the graphs anymore because I changed dev machines and nothing worked anymore. But the exact phase relationship changes if there is a phase shift applied to the discontinuity as part of low passing it and not to the actual sine wave bit. Again, this isn't a problem, right? You can get, well, it's not a deal breaker. Again, the way you do this is you get your low passed, sorry, you get the version we have here, and you get the high passed version that aliases, and then you'd add the high passed one into your original, subtract the high passed one from the original, and then you'd phase shift that so they match. So this is solvable, it's just a little fiddly, again. So if you can, just approximate your sine wave as a really accurate polynomial, then in some ways your life is a lot easier because everything stays in phase, and the more things that are just polynomials, the more you can apply to this. And yeah, so what I've posted on GitHub is just the basic ingredients. You've got a bunch of parallel filters, you move them along in time, you add different impulses or steps or whatever, and this could be wrapped up into a nice interface for polynomial oscillators, or hard sync and phase modulation, or waveshaping, or resampling. And I haven't done all of those yet, and I probably won't get around to all of them. But the base maths of this, the base technique, is, I think, very cool. And I think quite simple if you've got that whole discrete and continuous time thing going on in your head. And that actually is all the talk that I have. So this is me. Get in touch with me if there are any questions that don't manage to get covered here, or if there are any interesting, crunchy DSP problems that I could take a swing at. I have to keep giving these talks because people only ask me questions they've seen me answer in presentations, so that's why I'm here. I'm joking. But yeah, just get in touch about anything. And yeah, I think that's it. Any questions?